During the air war over Europe, American heavy bombers became a familiar and dangerous sight in the skies above German territory. Large formations of aircraft crossed the continent almost daily, carrying enormous bomb loads aimed at factories, railways, oil facilities, and military bases. Among these aircraft, one bomber in particular appeared again and again in German reports and combat encounters, the B-24 Liberator. German fighter pilots frequently intercepted these bombers during their missions, attacking them as they approached their targets, or during the long journey back toward Allied bases. Many B-24s were destroyed during these battles, but usually the wreckage that fell to the ground was badly damaged or scattered across wide areas, making it difficult for engineers to study the aircraft in detail. For German aviation engineers, this was frustrating. They wanted to understand how the Americans had designed such a long-range bomber, and why so many of them seemed to appear in the skies over Europe. Photographs and intelligence reports could reveal some details, but nothing compared to having an intact aircraft to examine directly. Every aircraft design contained secrets hidden within its structure. Details about the wing design, the internal framework, the engines, and the production techniques used to build it. Without a complete aircraft to study, many of those secrets remained difficult to uncover. Eventually, German forces obtained exactly what they had been hoping for: a captured B-24 that had landed or crashed without being completely destroyed. In some cases during the war, a damaged Allied aircraft were forced to make emergency landings in German-controlled territory. When that happened, the aircraft often fell into German hands, with large portions of its structure still intact. This created a rare opportunity for engineers and technical specialists who were eager to study the enemy's technology. When news spread that a B-24 Liberator had been captured in relatively good condition, German aviation engineers quickly moved to inspect it. For them, this was more than just a curiosity. It was a chance to examine one of the most important American bombers of the war up close. Every section of the aircraft could provide valuable information: how the wings were constructed, how the engines were mounted, how the defensive guns were arranged, and how the fuselage was reinforced to carry heavy bomb loads across long distances. As they began examining the aircraft piece by piece, the engineers realized they were not just looking at another bomber. They were looking at an aircraft that represented something much larger. Hidden within the design of the B-24 was a glimpse of the industrial system that had produced it, and that system would reveal something about how the United States was fighting the war on an entirely different scale. When German engineers began studying the captured aircraft, they already knew that the B-24 Liberator played a major role in the Allied bombing campaign. Reports from fighter pilots and air defense units had mentioned the bomber repeatedly during missions over Europe. Large formations of these aircraft appeared over German territory, alongside other heavy bombers carrying enormous loads of explosives and flying long distances from bases in Britain and other Allied-controlled areas. For the German military, understanding the aircraft was not simply a technical curiosity. It was directly connected to defending the country's skies and protecting critical industrial targets. The B-24 had been designed as a long-range heavy bomber, capable of traveling farther than many other aircraft in its class. This range allowed it to strike targets deep inside enemy territory and still return safely to base. In the vast geography of World War II air warfare, range mattered enormously. A bomber that could fly hundreds of additional miles could reach factories, oil fields, and transportation networks that might otherwise remain safe from attack. German air defense planners had already learned how destructive the Allied bombing campaign could be. Factories that produced aircraft engines, tanks, and ammunition were essential to sustaining the war effort. If those facilities were damaged or destroyed, the effects could spread throughout the entire military system. Railways, oil refineries, and industrial complexes were especially vulnerable to heavy bomber attacks. And the B-24 was particularly dangerous because it could carry a large bomb load while flying at high altitude in organized formations. These formations were designed to protect the bombers from enemy fighters. Each aircraft carried multiple defensive machine guns, allowing the bombers to support one another during attacks. A fighter pilot approaching the formation often faced concentrated defensive fire from several aircraft at once. This defensive strategy forced German fighters to attack quickly and carefully. Pilots often approached from angles where the defensive guns were less effective, firing bursts of cannon fire before pulling away. Even so, attacking a bomber formation was extremely dangerous work. For engineers examining the captured aircraft, the B-24 represented more than a single bomber. It was part of a massive Allied strategy built around long-range bombing operations. Every feature of the aircraft had been designed with that mission in mind. Its range, its bomb capacity, and its defensive weapons all reflected the requirements of strategic air warfare. But as German engineers looked closer at the aircraft itself, another question began forming in their minds. The bomber was impressive, but the real mystery was not just how it performed. The real mystery was how the United States was producing so many of them. When the captured B-24 was finally moved to a secure airfield for examination, German engineers and aviation specialists began studying the aircraft with intense curiosity. For them, this was a rare opportunity. Normally, the bombers they encountered in combat were either destroyed in midair or crashed in such a way that much of the structure was damaged beyond useful analysis. But this aircraft, though not perfectly intact, still contained enough of its structure to reveal how the Americans had designed and built one of their most important bombers. The inspection began with the most visible components of the aircraft. Engineers walked around the bomber slowly, examining the fuselage, wings, landing gear, and engine nacelles. They carefully measured the wingspan and studied the unusual shape of the aircraft's wing design. Compared to many European bombers, the B-24 had a long, narrow wing that looked very different from the broader wing shapes commonly used in German aircraft. Inside the aircraft, the engineers examined the cockpit and the arrangement of instruments and controls. They noted how the pilot and co-pilot positions were arranged and how the flight systems were organized. Every switch, cable, and mechanical linkage was carefully observed. Even small design decisions could reveal important ideas about how American engineers approached aircraft construction. Moving further into the aircraft, they studied the bomb bay located within the fuselage. The B-24 was designed to carry a heavy load of bombs while still maintaining the range needed for long missions. And engineers looked closely at the structural supports that allowed the aircraft to carry this weight without compromising its ability to fly safely over long distances. The defensive gun positions attracted particular attention. The bomber carried multiple machine gun turrets positioned around the aircraft to defend against fighter attacks. German engineers inspected these turrets carefully, examining how they rotated, how the gunners were protected, and how ammunition was fed into the weapons. They understood that bomber formations relied heavily on defensive firepower to protect themselves from interception. But as the inspection continued, something else began to stand out. The aircraft's construction revealed a pattern that engineers found both impressive and surprising. Many sections of the aircraft appeared to be built in ways that suggested they could be manufactured separately and assembled later. Panels, internal structures, and mechanical components were arranged with a kind of practical efficiency that hinted at something beyond the aircraft itself. The B-24 was not just designed to fly well. It was designed to be built quickly, and the more the engineers examined the aircraft, the more they began realizing that the real secret of the bomber might not lie in its weapons or engines, but in the way it had been manufactured. As the German engineers continued studying the captured bomber, their attention gradually shifted away from individual components and toward the overall design philosophy behind the aircraft. At first glance, the B-24 Liberator appeared complex, with its multiple gun positions, large wings, and 4 powerful engines. But when they began looking closer at the way the aircraft had been assembled, they noticed something unusual. Many parts of the bomber were designed in sections that could be produced separately and then assembled together later. Instead of relying on highly customized parts that required careful hand construction, many components seemed standardized and organized in a way that simplified manufacturing. Panels, their structural frames, and equipment mounts appeared to follow consistent patterns that could be repeated easily during production. To an experienced engineer, this was an important clue. Aircraft built in this way were not just designed for performance. They were designed for speed of production. The engineers began realizing that the Americans had approached bomber construction with a very different philosophy from the one used in many European aircraft factories. In Germany, aircraft production often relied on skilled craftsmen assembling complex structures with great precision. Many aircraft designs required careful manual work, and even small changes in design could slow production. The process produced excellent aircraft, but it was not always ideal for building extremely large numbers of machines in a short period of time, and the B-24 seemed to follow another approach entirely. Its structure suggested that large portions of the aircraft could be manufactured in separate facilities and then brought together for final assembly. Wings, fuselage sections, and internal components appeared arranged in ways that would allow workers to install them quickly on an assembly line. Even the placement of certain mechanical systems seemed organized to simplify maintenance and replacement. For the German engineers studying the bomber, this discovery was both impressive and concerning. The aircraft itself was certainly capable, but the real significance lay in the system behind it. If the United States had designed the bomber specifically to be built in large numbers, it meant American factories could produce far more aircraft than their enemies might expect. And the evidence for this possibility was already visible in the skies over Europe. Day after day, formations of American bombers continued appearing over German territory. Even when fighter pilots succeeded in shooting some of them down, the next mission would arrive with just as many aircraft as before. Standing beside the captured B-24, the engineers began realizing that they were not simply studying a single enemy bomber. They were studying the product of an industrial system built to produce aircraft on a scale the world had rarely seen before. While examining the aircraft's structure, German engineers soon focused their attention on one of the B-24 Liberator's most distinctive features, its wings. Compared to many bombers built in Europe during the same period, the B-24's wings looked unusually long and narrow. Their shape gave the aircraft a very different profile when viewed from the ground or from another aircraft in flight. This was not simply a visual difference. The wings were built using a special aerodynamic design known as the Davis wing. The shape of this wing allowed the aircraft to generate lift very efficiently while flying at higher speeds and altitudes. For a bomber designed to travel long distances carrying heavy loads, this efficiency was extremely valuable. The design helped reduce drag while still providing enough lift to keep the aircraft stable in the air. For the engineers studying the captured bomber, this wing design explained several things they had already observed during combat reports. German fighter pilots had often reported that the B-24 could travel long distances and appear over targets far from its bases. The Davis wing helped make this possible by improving the aircraft's fuel efficiency and allowing it to remain airborne longer. But the wing also introduced certain structural challenges. Because it was long and relatively thin compared to other bomber wings, it required careful engineering to maintain strength. Engineers studying the aircraft examined the internal framework of the wings, looking at how the metal spars and structural supports were arranged. These internal structures were designed to carry the weight of the engines, the fuel, and the heavy loads the aircraft carried during bombing missions. What they saw inside the wing revealed the same design philosophy they had noticed elsewhere in the aircraft. The internal components were arranged in ways that balanced strength with manufacturing efficiency. The structure was strong enough to support the aircraft's demanding missions, yet it was also organized in a way that allowed sections to be produced consistently during large-scale manufacturing. The 4 engines mounted along the wings also contributed to the bomber's performance. With 4 powerful engines working together, the B-24 could maintain flight even if one engine was damaged. This increased survivability during combat missions when the aircraft might be hit by anti-aircraft fire or attacked by enemy fighters. And German engineers studying the wing realized that this part of the aircraft was not just important for flight performance. It also reflected the broader strategy behind the bomber's design. The B-24 had been engineered to fly far, carry heavy loads, and remain in the air even under difficult conditions. And those capabilities made it one of the most effective long-range bombers used by the Allies during the war. As the German engineers continued their examination of the captured B-24 Liberator, they turned their attention to another critical feature of the aircraft: its defensive armament. Heavy bombers flying over enemy territory faced constant threats from fighter aircraft and anti-aircraft guns, and the designers of the B-24 had clearly expected these dangers. The bomber carried numerous machine guns positioned around the aircraft so that attackers approaching from almost any direction would face defensive fire. The engineers inspected each gun position carefully. The nose of the aircraft contained forward-facing weapons that could fire at enemy fighters approaching head-on. Along the top of the fuselage, a rotating turret allowed a gunner to defend the aircraft from attacks coming from above. Yet additional guns were mounted along the sides of the aircraft, covering the areas where fighters might attempt to approach from the flanks. One of the most important defensive positions was located at the rear of the aircraft. The tail turret allowed a gunner to fire directly at enemy fighters attempting to attack from behind. This position was especially important because many fighter pilots preferred to approach bombers from the rear, where the target appeared largest and easiest to hit. When these weapons were combined in a bomber formation, the result was a powerful defensive network. A single B-24 already carried significant firepower, but when dozens of bombers flew close together, their guns overlapped in coverage. Enemy fighters approaching the formation could suddenly find themselves facing machine gun fire from several bombers at once. German fighter pilots had already experienced this danger during combat missions. Interception reports frequently described intense defensive fire coming from American bomber formations. Pilots attacking the bombers had to move quickly, firing their weapons during short attack passes before pulling away to avoid sustained gunfire. Staying too long within range of the bomber's defensive guns could be extremely dangerous. The engineers examining the aircraft understood how this defensive strategy worked. The bomber was not meant to fight alone. Its design assumed that it would operate within a large formation of similar aircraft, each protecting the others with overlapping fields of fire. Then this concept created a difficult challenge for defending fighter forces. Shooting down a bomber required skill, speed, and precise attacks. Even when fighters succeeded in destroying individual aircraft, the formation itself often continued toward its target. As they inspected the gun mounts and ammunition systems, the engineers recognized that the B-24 had been designed to survive in hostile airspace long enough to complete its mission. But the more they studied the bomber, the clearer it became that the aircraft's effectiveness was not based on weapons alone. Its true strength was connected to something much larger than the aircraft itself. As German engineers finished examining the aircraft's structure, its wings, and its defensive weapons, a larger realization slowly began to emerge. The B-24 Liberator itself was certainly impressive, but the aircraft alone was not the most important discovery. The more troubling question was how many of these bombers the United States seemed capable of producing. By the middle years of the war, American bomber formations over Europe were growing larger and more frequent. Missions often involved dozens or even hundreds of heavy bombers flying together toward their targets. Even after fierce fighter attacks and heavy anti-aircraft fire, new bomber formations continued appearing over German territory. For German planners, this raised a critical concern. Even if a number of bombers were destroyed during each mission, the Americans seemed able to replace them quickly. The captured B-24 provided a clue as to why this was possible. The aircraft had clearly been designed with large-scale industrial production in mind. Many components could be manufactured in separate factories and then transported to final assembly lines where the aircraft would be completed. This type of production system allowed different parts of the bomber to be built simultaneously in multiple locations. Instead of relying on slow, handcrafted assembly, the Americans were using techniques similar to modern industrial manufacturing. Workers could specialize in producing particular sections of the aircraft, repeating the same tasks efficiently over and over again. One of the most striking examples of this system was the massive Willow Run factory in the United States, and this enormous facility was specifically built to produce B-24 bombers in huge numbers. At its peak, the assembly line there was capable of producing a complete bomber in a remarkably short amount of time. For German engineers accustomed to more traditional aircraft production methods, this scale was astonishing. Factories in the United States were operating on an industrial level that far exceeded what most nations could achieve during wartime. Raw materials, engines, weapons, and structural components were flowing into these factories continuously, allowing production lines to operate almost without interruption. The captured B-24 therefore represented more than just a single bomber. It was a product of an industrial system capable of building aircraft faster than many opponents could destroy them. This realization had serious implications for the air war over Europe. Shooting down bombers was still possible, but replacing lost aircraft was becoming easier for the Allies than for their enemies. Standing beside the captured Liberator, the engineers began understanding something that was becoming increasingly clear across the battlefields of the war. The conflict was not only being decided by tactics or individual weapons, it was also being decided by the immense industrial strength behind them. As German engineers finished their detailed study of the captured B-24 Liberator, the conclusions they began drawing extended far beyond the aircraft itself. The bomber revealed important information about American engineering, but even more importantly, it revealed something about the scale of the industrial effort behind the Allied war machine. The aircraft they were examining was only one example among thousands that were already flying over Europe and other battlefronts. For the German military, this realization carried serious implications for the future of the air war. The B-24 was not simply an advanced aircraft. It was a product of an industrial system capable of sustaining long and demanding bombing campaigns. By this stage of the war, the Allied bombing offensive had become a constant pressure on German industry. Day after day, formations of heavy bombers crossed the skies over occupied Europe and Germany itself. These aircraft targeted factories, rail networks, oil refineries, and transportation hubs that were essential to the German war effort. Each attack forced resources to be diverted toward repairs, air defenses, and emergency measures to keep production running. Even when bombers were shot down, the next wave of aircraft would arrive soon afterward. The captured B-24 helped explain why this cycle continued. The United States had organized its production system to replace losses quickly. Engines, weapons, electronics, and structural components were all manufactured in enormous quantities by different factories working together. Assembly plants then brought these parts together to build complete aircraft. The result was a steady flow of bombers entering service faster than many opponents expected. For German strategists, this created a difficult situation. Air defenses could destroy some bombers, and fighter pilots could intercept many more. But stopping the bombing campaign entirely required reducing the number of aircraft reaching German skies. If American factories could continue producing bombers at such a rapid pace, the Allied air forces would always have enough aircraft to continue their missions. The B-24 therefore symbolized something larger than its own design. It represented the industrial capacity that allowed the United States to sustain a massive air war across multiple continents. Even if individual aircraft were lost, the overall strength of the bomber fleets remained intact. Standing beside the captured Liberator, the engineers began to understand that the challenge facing Germany was not only technological or tactical. The war in the air was also becoming a contest of production, logistics, and industrial strength. And in that kind of contest, the nation capable of building the most machines often gained the decisive advantage. By the time German engineers completed their examination of the captured B-24 Liberator, the aircraft had already revealed far more than its mechanical details. They had studied its engines, its wings, its defensive weapons, and its internal structure, but the most important lesson came from the larger picture surrounding the bomber itself. The B-24 was not simply an effective aircraft used by the Allies during the war. It was one piece of an enormous industrial system that was capable of producing weapons, vehicles, and aircraft on a scale few nations could match. The Liberator represented the kind of machine that could only exist when engineering design and industrial production were working together at an immense level. As the war continued, the number of B-24 bombers appearing in combat kept growing. If these aircraft were used not only in Europe, but across multiple theaters of the war, including the Mediterranean, the Pacific, and operations over long ocean routes. The bomber's long range made it valuable for missions that other aircraft could not easily perform, and its heavy payload allowed it to strike important targets deep inside enemy territory. Entire groups of these bombers operated together in formations that filled the sky, carrying out strategic bombing missions that became a central part of the Allied war effort. By the end of the war, the B-24 Liberator had become one of the most produced heavy bombers in history. Thousands of these aircraft were built in American factories, and they served in many different roles beyond traditional bombing missions. Some were adapted for maritime patrol, others for transport duties, and many were used in long-range reconnaissance operations. Their versatility made them one of the most widely used aircraft of the conflict. For the German engineers who had studied the captured bomber earlier in the war, the aircraft offered a clear insight into how the United States approached modern warfare. The Liberator demonstrated that victory in a global conflict depended not only on the design of weapons, but also on the ability to produce those weapons in overwhelming numbers. A well-designed aircraft was important, but the industrial system capable of building thousands of them was even more significant. In the end, the B-24 Liberator was more than a bomber flying over enemy territory. It was a symbol of the enormous industrial capacity that powered the Allied war effort, and the engineers who inspected the captured aircraft had hoped to learn about an enemy machine. Instead, they had glimpsed the larger force behind it, a production system capable of filling the skies with bombers faster than many opponents could stop them. The captured B-24 revealed more than just an enemy aircraft. It showed the industrial power that allowed America to fill the skies with bombers. In modern warfare, victory was not decided only by weapons or tactics, but by the ability to build them faster than the enemy could destroy them. And the B-24 Liberator was one of the clearest symbols of that power.